Deep neural networks have a problem. It's quite a famous problem by now. If you take an input to a deep neural network, such as this image of a panda, for example, you can make an imperceptibly small change to it, and it will be classified incorrectly. You can do this by computing just the right tweak to each individual pixel in the image. Most methods for the testing of deep neural networks use these pixel tweaks to generate test inputs, but there is a significant limitation of this approach. To understand this shortcoming, consider a faulty deep neural network that looks only for tongues. So if a dog has its tongue out, it gets classified as a golden retriever, no matter its true breed. And if a dog doesn't have its tongue out, it gets classified as a German Shepherd, no matter its true breed. This tongue example is just for illustration, but classifiers picking up on spurious correlations like this is a real problem that can cause deep neural networks to rely on incorrect features like this. Now, let's imagine we don't know that this deep neural network has this problem. We hope that our testing process will reveal any faults. But imagine testing this deep neural network using a pixel tweak approach. By definition of a pixel tweak, the change will be imperceptible. There is no way that we can understand the classifier's inappropriate reliance on tongues just by tweaking individual pixel values. We won't be able to see it. So testing using existing pixel tweak methods cannot detect the fault in this deep neural network. In this talk, I'll describe a new approach to testing deep neural networks that can detect faults such as this. In this example, our method starts with an image that is correctly classified as a golden retriever and tweaks it so that it is incorrectly classified as a German Shepherd. But rather than making imperceptible tweaks to individual pixels, our method tweaks high-level features of the image. In this case, as our method tweaked the image to make it incorrectly classified, it removed the tongue of the dog. So this particular test case revealed the fault in this particular deep neural network. Of course, our method works not just for this particular test input and not just this faulty deep neural network. But before looking closely at our results, let's look at how our method actually works. I'm Isaac Dunn, and I'm presenting our paper exposing previously undetectable faults in deep neural networks. You're probably familiar with deep neural networks. They're machine learning systems where the parameters are the strength of connections between different nodes known as neurons. And in this example, the input features are the pixels of an image, and the output is predictions of which label best fits the image. The promise of deep learning is that neural networks should learn a hierarchy of useful features, and this is going to be important for understanding our method. So consider our image classification example. Of course, real neural networks may have many more layers and more neurons than this, but it's just simplified for illustration. But the point stands that in the early layers, the idea is that the raw input features, so the pixels in this case, are composed together into learnt, useful, low-level features such as edge detectors or color detectors maybe. And then the hope is that these low-level features are learnt to be composed into medium-level features such as eye detectors or nose detectors, and that these in turn are combined to give the high-level features associated with the outputs. In this way, deep neural networks are intended to learn a hierarchy of useful features from low-level to high-level, and so these don't have to be coded by hand. Do deep neural networks really work like this in practice? Well, there's some interesting evidence that yes, they really do. For example, this car detector neuron on the right seems to be composed of window, car body, and wheel detector neurons in the appropriate way. But discriminative models like the classifiers we've been talking about so far are not the only kind of deep neural network. In our method, we make use of generative models. Whereas an image classifier network takes an image and predicts its label, a generator network takes a label and generates an image. How exactly generative networks are trained isn't important for our purposes. Instead, we will just use a generated deep neural network that has already been trained. That means we can use it to generate samples that are drawn from an approximation of the distribution of training images. So it can generate us new realistic images. Generator networks are reverse classifiers in that they have reversed inputs and outputs compared to a classifier. But also the kinds of feature representations inside the generator network are the reverse in order of those in the classifier. So the early layers of the generator encode high-level meaningful features, which gradually become finer grained and lower level until at the output layer, individual pixel values are output. That's the reverse way around to a classifier. Our method exploits this hierarchy of useful feature representations inside trained generator networks. As a precursor to our method, consider performing pixel tweaks to a generated image. First, we pick a random input to the generator network. Then, this is passed through the generator network to get the pixels of the generated image. This in turn is the input to the classifier network that we're testing. When the classifier output is known, the standard backpropagation algorithm can be used to define the derivative of the classifier output with respect to each pixel value in the image. And that gradient information then determines the tweak that should be made to each pixel, so that eventually the tweak can be made and we end up with an image for which the classifier gives an incorrect output. Now we're in a position to introduce our method. Rather than making tweaks to the individual pixels, we can backpropagate the gradient information from the classifier to the internal activation values inside the generator. Because these activation values at different layers encode different useful features of the generated image, tweaking these instead of the pixels results in changes to meaningful features of the generated image. In this way, we generate test inputs by making tweaks to these meaningful features until the classifier's output is incorrect. Here are some examples of the kinds of features that our method can tweak. The original generated image is at the top, with the tweaked test input that the classifier gets wrong below. So on the left, you can see the position of the snake has been tweaked so that it gets classified as a crossword. Then the shape of the mushroom has been tweaked so that it gets classified as a hair slide. The colour of the Pomeranian has been tweaked so that it gets classified as an American lobster. The texture of the background in the picture of the robin has been tweaked so that now it gets classified as a keyboard. And the structure and contents of this bookcase has been tweaked so that it gets classified by the classifier incorrectly as a soup. In evaluating our method, we asked these three research questions. First, can this method detect artificially injected faults in deep neural networks? Second, can our method detect faults in state-of-the-art deep neural networks? And lastly, can this method detect faults that prior methods cannot? Let us look at our results for research question 1. But first we need to understand how we injected faults into deep neural networks. So to inject a fault into a deep neural network, we use a hand-curated biased training dataset. So for example, to create a classifier that distinguishes golden retrievers and German shepherds based just on whether the tongue is out or not, we manually created a data set of these dogs split by whether the tongue was out or not, and then trained a deep neural network on this data set. Given a deep neural network with such a fault deliberately injected, we generated tests for it. Remember that these tests are just optimized for the classifier to give the incorrect output for that image. So there's nothing to do with tongues, in this case, hard-coded. So the tongue being out in the tweaked, optimized test input is an indication that the classifier is relying on that feature when it shouldn't be. Not every test input reveals the presence of the fault though, so in this example, the tongue is out in both cases, so the classifier's over-reliance on tongues isn't indicated by this test case. And here is another example of a test case that does reveal the fault because the tongue has been removed in the tweaked test input. Of course, we didn't create just one deep neural network with an artificially injected fault. So this example shows a test case revealing another classifier's over-reliance on colour saturation to distinguish Alps from volcanoes. This test case indicates a classifier's reliance on the weather to discriminate between palaces and castles. Here, the test case reveals an over-reliance on grass or snow in the background to distinguish wolves from huskies. And this generated test case shows the inappropriate reliance on leaves to discriminate between oranges and lemons. In all, we tested 8 different deep neural networks listed here, for which we introduced an artificial fault. For each, we counted the number of generated tests that revealed the presence of the injected fault. It was as low as 15% for some deep neural networks and as high as 91% for others, with most somewhere in between. But the important point is that our testing method did detect the faults in far more than 0% of tests, whereas pixel tweak tests, for example, could never detect the presence of these faults because they're constrained to imperceptible tweaks to individual pixels. You're never going to be able to see these, detect these more meaningful problems. Of course, our method isn't the first to look at more meaningful changes than pixel tweaks, but existing semantic approaches can only manipulate hand-selected features, such as, in this case, the various corruptions shown, or other works manipulate the color or the texture or the rotation of an image. But for these two, 0% of tests could detect faults such as reliance on a dog's tongue or on a lemon's leaves, unless those manipulations were hand-coded, because these, even though they're more meaningful than the pixel tweaks, they're constrained to only be the particular kind of meaningful change that has been hand-coded. In contrast, our method is able to detect such problems as the reliance on the dog's tongue or lemon's leaves because it can manipulate features learned from data. So our method can detect faults artificially injected into deep neural networks. But let's look now at state-of-the-art deep neural networks. We used our method to generate hundreds of tests for the state-of-the-art ImageNet classifier, which is the standard image classification benchmark, and that classifier was the EfficientNet B4. And we were able to successfully generate hundreds of failing test cases, but our method's ability to generate new tests that the classifier gets wrong isn't impressive in itself, since existing methods can do this just as easily. The question is, can our method generate usefully different kinds of tests to existing approaches? These two graphs show that if our tests are measured as if they were pixel tweaks, their size, in blue, is much larger than the standard pixel tweak sizes, in red. And note that you can't just increase the size of pixel tweaks allowed, you can't just move the red line to the right, because without targeting them to meaningful changes, it could destroy the image. But in fact, even showing that the tests that are generated by our method are different than those that come from pixel tweaks, that's not enough. For example, it could be the case that our tests were just detecting the same problems as the pixel tweak tests, in which case our testing method wouldn't actually be adding any value. It wouldn't be detecting any new faults. So we conducted an experiment to see whether our tests were detecting a different kind of fault than those detected by pixel tweaks. So first, we generated a test input for the state-of-the-art model, the EfficientNet. Then we took that same test, optimized for the state-of-the-art model, and passed it to a deep neural network trained to be robust to pixel tweaks. And we found that 74% of these tests generated for the state-of-the-art model also were failing test cases on pixel-robust models. So the pixel-robust models also gave an incorrect output. This suggests that our tests are detecting a different kind of fault than those detected by pixel tweaks. Crudely, that's because faults detected by pixel tweaks exist in the state-of-the-art model, but not in the pixel-robust model. In summary, our new test generation method works by manipulating the meaningful features learned by a pre-trained generator network. This means that the generated tests are able to detect artificial faults in deep neural networks, whereas existing methods cannot detect these faults at all. And when our method is used to evaluate state-of-the-art deep neural networks, the tests indicate the presence of faults not detected by existing methods. So it's a different kind of fault than those found by existing tests. Looking to the future, it's important that we continue to develop our approaches to the testing of deep neural networks if we're ever to fully understand their limitations and trust them in important contexts. We expect that the manipulation of learnt features, as in this paper, has an important role to play. Thank you. I hope you found this talk useful, and I'll be glad to answer any questions you have.